Welcome. In today's video, we're going to be deriving the maximum likelihood estimates for the scale parameter of a Weibull distribution given a known value of the shape parameter. So let's begin. First, let's define our problem, which is suppose we have a series of random variables x1, x2, xn, and they are all independently and identically distributed with a Weibull distribution. And I'm going to say that it's a Weibull distribution with a shape parameter lambda and scale parameter lambda. Then the PDF, or the probability density function of xi, is given by the following. So it would be f subscript x xi given a gamma lambda is equal to gamma on lambda xi all over lambda to the power of gamma minus 1 e to the power of xi on lambda to the power of gamma. And this is true for xi greater than or equal to 0. However, this is a little bit of a complicated form of the distribution, so I'm actually going to reparameterize it a little bit, and here's another version of the parameterization. And I'm going to just say let theta equal lambda to the gamma. And so now we have a new parameterization. We have fx of xi given gamma theta now is equal to, it will become gamma on theta xi to the gamma to the power of minus 1 exp or e to the power of negative xi to the gamma on theta. And this is a little bit more of an easier parameterization to deal with when deriving maximum likelihood estimates. So from here we can define the likelihood function, and the likelihood function, recall, for gamma theta given a set of data x is given by the product of I equals 1 to n of the respective probability density functions evaluated at each of the data points. We can then say that is equal to I equals 1 to n. We can take our copy of the distribution, copy, paste, and we have it here. And we're going to multiply that from I equals 1 to n. The next step is to recognize that we can break it up into respective terms. So for the first component, we can say that's I equals 1 to n of gamma on theta times I equals 1 to n of xi to the gamma minus 1 times, and then for this exponential, we've still got the exponentials at the end, I equals 1 to n of exp of negative xi to the gamma on theta, close the bracket. So for this first term here, although this particular expression here doesn't depend on the index I, we still have the fact that we're multiplying from I equals 1 to n. In other words, we're actually just multiplying what's inside this product n times. So that actually leaves us with gamma on theta all to the power of n for the first term. For the second term, we can actually sort of simplify it slightly in that we notice in this particular instant, in fact, let me do one line of working to show you exactly where I'm coming from. So I'm just going to expand out this product here. So this would give me x1 to the gamma minus 1 times x2 to the gamma minus 1 times dot 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 times xn to the gamma minus 1 in that second set. And then finally we have here again the product of exponentials. So I'm going to write that down. Now I'm going to write it in the e form, e to the xi on theta gamma, x1, apologies. That's x1 to the gamma times e to the negative x2 to the gamma on theta times dot 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 times e to the negative xn to the gamma on theta. And sorry that I keep transitioning between e's and exponentials, but hopefully you can follow along. So for the first term, we still no change for this particular gamma on theta. So we're just going to rewrite gamma on theta to the power of n. For these terms here, notice that this is the equivalent of, because they all have the same power, we can actually take the power outside of the multiplication. So then this becomes x1 times x2 times dot 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 times xn all to the power of gamma minus 1 times. Similarly, we can use some sort of similar power law here where we've got the same base, the consistent base, E, which means we can actually, because we have the same base, we can now just add all these components together. So that would give us all e to the negative x1 on theta gamma minus x2 to the gamma on theta minus dot 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 minus xn to the gamma on theta at the end. Simplifying in this final step gives us the first term as unchanged, so I'm going to write gamma on theta to the power of n times, here what we have is a product of terms, and I'm going to simplify it and put it in a compact form, giving us I equals 1 to n of xi, product of I equals 1 to n of xi to the gamma minus 1. And then here our exponential terms, we can take out a common factor of negative 1 over theta. So e to the negative 1 over theta, and now we're going to take, we've got x1 to the gamma plus dot 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 all the way to plus xn to the gamma here. And then in a final sort of form, that becomes gamma on theta unchanged to the power of n times the product of I equals 1 to n of xi unchanged to the gamma minus 1. And then in a nice compact form, again, we've got e to the negative theta sum of I equals 1 to n of xi to the gamma. Cool. And I'm going to take that copy that function just for later. Copy. So now that we've established that, we can derive the log likelihood function. So the log likelihood function of gamma theta given our data x by definition is equal to the log of the likelihood function gamma evaluated here, which in this case is log of, paste this all in, of our likelihood function that we derived before. Now, we know properties of logs, that when you have log of a product of terms, that is equal to the sum of those respective terms. So this gives us log of the first term, theta or gamma on theta to the power of n, plus log of the second term, product of I equals 1 to n of xi all to the power of gamma minus 1, plus, and finally, log of e to the negative 1 on theta, sum of I equals 1 to n of xi to the gamma, all close bracket. Now, again, properties of logs. When you have a power inside the log, the power can come out the front. So that gives you n log gamma on theta. Similarly, we have a power here, so that can come out the front of the log. So that gives us plus gamma minus 1 in brackets log of the product of I equals 1 to n of xi. And here we've got a nice particular formation in that we've got log of an exponential. And when you take log of the exponential, you're just left with basically the power inside that exponential. So that collapses to minus 1 on theta, the sum of I equals 1 to n of xi to the gamma. In the next step, we can do one last bit of simplification here, in that n log of theta, or more importantly, log of gamma on theta can be rewritten as log gamma minus log of theta, or at least this component here, but we still have the n out the front, so we've got n log gamma minus n log theta. Then here we still have the gamma minus 1, so we've got plus gamma minus 1. And one of the properties of logs, if you recall, is that log of a product of terms is equal to the sum of the log of those terms. So in other words, this simplifies to the sum of I equals 1 to n of the log xi's. And then, of course, we still have our minus 1 on theta. I equals 1 to n of xi to the gamma. Cool. So, now that we've derived that log likelihood function, what we need to do is we need to compute the derivatives of this log likelihood function, because that will allow us to determine the maximas and the minimas of the function itself. Now, in this particular problem, the setup I gave was that we had a known value of gamma. So all we need to do is we only need to differentiate with respect to theta. However, for completeness, I'm going to present you with the derivatives also with respect to gamma, partially for your own interest, but also partially because at the end of this video, I'm going to come up with an equation which needs to be solved numerically, say if gamma was unknown, as well as theta. So, let us begin. First, let's take partial derivatives with respect to theta. So, the partial derivative of the function of our log likelihood, not with respect to lambda, but gamma theta, given our data x, is given by the following. So, we need to take the partial derivative of this whole, this whole term up here. Copy that, paste, here it is. The only distinction is I'm just going to instead rewrite this 1 on theta. I'm going to rewrite that as minus theta to the negative 1. And that's just going to allow us to do our differentiation a little bit easier. So, for the first term, this term here doesn't depend on theta, so it collapses to 0. Nothing to be done. Our second term here, we know that log of theta, when differentiated with respect to theta, gives us 1 on theta. So this term here becomes minus n on theta. Our term here, our fourth term in this equation, doesn't depend on theta, so differentiated, it collapses to 0. And finally, this last term does depend on theta, and we've got a power now. So we know that when we've got a power, we need to bring that power to the front. So that -1 and the minus at the front become a positive, and then we have to subtract 1 off the power, and that'll give us -2. So it'll be theta to the -2, I equals 1 to n of xi to the gamma. Cool. Now again, we're going to rewrite this, or we're going to find the second derivative with respect to theta. So we'll go dn gamma theta given our data, and we'll put that in brackets. D theta is equal to, in this particular instance, the partial derivative of, now this term here, it's the partial derivative with respect to the first partial derivative. So we'll put it in here. The only distinction, of course, in this particular instance, I'm going to rewrite my n on theta out the front here to n theta to the -1, again allowing us to differentiate a little bit easier. So let's do that now. And what do we get when we arrive at this particular function? This gives us, in this particular instance, you got -1 comes down the front. That gives you a positive. And then you've got to take 1 off the power, so it becomes -2. For this particular case here, you've got a -2. That -2 needs to come down the front. -2, 1 off the power gives you -3. And you still have just this factor of xn xi to the gamma out the front. And for simplicity, I'm going to write that as n on theta squared minus 2 on theta cubed, sum of I equals 1 to n of xi to the gamma. Brilliant, 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 brilliant. So we've done that. We now need to evaluate the partial derivatives with respect to gamma, out of interest, really, at this stage. So go there. D gamma is equal to D on D gamma of, let's take our likelihood function that we evaluated before. Here it is. Copy that down, and brilliant. Okay, I'm gonna just rewrite it so it all fits on the screen. So for the first term here, it does depend on gamma, and in fact we know derivative of log is 1 on the inner function, so that becomes n on gamma, quite simply. The second term doesn't depend on gamma. Differentiated with respect to gamma is not an issue for us. So it collapses to 0. This one here, there is a gamma here. It's got a gamma and it's technically got a constant of this out the front. So when factoring this out, this would give us plus the sum of I equals 1 to n of log xi, and that's it. Then minus, in this particular instance, you can take the partial differentiation. Because it's a product times a sum, you can actually take that partial differentiation through the product and through the sum to give you minus 1 on theta sum of I equals 1 to n of the partial derivative with respect to gamma of xi to the gamma. And then our final step here, n on partial derivative plus I equals 1 to n log xi minus 1 on theta. Now, the derivative of xi to the theta, it is not technically, it's not e to the theta, so it doesn't just become itself. We actually arrive at this particular identity, the derivative I equals 1 to n. And as a side note, I might just show you the proof of why this is for your own interest. D on d gamma of xi to the gamma. We can think of this as d on d gamma of e to the ln xi to the power of gamma. All right, because if you take e to the ln xi, that will give you back your xi. This then becomes the partial derivative with respect to e to the ln xi theta, and I might move this up just a little bit for us. And now, because it's in the form e to the power of something times gamma, we know how to differentiate e at least. This is the scaling factor out the front, so that actually needs to come out the front. And so we've got is equal to ln xi e to the ln xi gamma. However, we know what e to the ln xi gamma is. It's just xi to the gamma. So that gives us left with ln xi to the gamma. And so that's just sort of the proof, a little bit of a proof of how we're going to derive, or we come to that particular derivative. So this becomes in a form xi to the gamma ln xi. And we've done our first derivative with respect to gamma. Now let's do our second derivative with respect to gamma. So we'll take this and we will take a copy. And so we note that the second derivative of the log likelihood function with respect to gamma is equal to the following. It is the partial derivative d on d gamma with respect to the terminology that we just came across before. Now, in this particular instance, this n on gamma we can rewrite as negative n on gamma. So far, so good. Sorry. Apologies, let me just rewrite. That n on gamma can be rewritten as n gamma to the negative 1. That's what I meant to say. And again, this xi to the lambda, similarly to before, we can rewrite this as e to the ln xi gamma. Right, and hopefully it's not too difficult to see that in the small writing that I've got. And then now when we take the partial derivative again, is for the first term, it's n gamma minus 1. What we need to do is we need to take the power down the front, 1 off the power. So it becomes negative n gamma to the negative 2. Second term doesn't depend on any gammas, so it cancels and drops to 0. This final term here again, minus 1 on theta sum I equals 1 to n. Again, we can take that partial derivative through the scaling factor and through the sum to give us d on d gamma, e to the ln xi gamma ln xi. And in this particular instance, this becomes, the first term at least nicely simplifies to n over gamma squared, which is nice. The second term here, 1 on theta, sum I equals 1 to n. Similarly as to before, we now need to take the scaling factor needs to come in front when you differentiate an exponential. We've already got the scaling factor actually out here once, so what we're left with is e to the ln xi gamma ln xi all squared, because we've differentiated twice. And then, of course, we can rewrite that e to the ln xi gamma simply as xi to the gamma. And there is our second derivative. And also, for interest, we can take the partial derivative, or the second partial derivative of the likelihood function in this particular instance with respect to theta and with respect to gamma. And in that particular instance, what could we do here? Here is our partial derivative. Which one's a little bit more complicated? Probably this one. Let's stick with this one here. This one might be easier to do. Copy. So this is the first derivative with respect to gamma. So then to take the second derivative with respect to theta and gamma, we just need to differentiate this with respect to theta. So I'm going to go to the other page now, and I'll say that that is d on d theta of, paste that in, this particular expression. Just noting, however, that this negative 1 over theta here, I'm going to write that as theta to the negative 1. So when we evaluate this, first term doesn't depend on theta, collapses to 0. Second term doesn't depend on theta, collapses to 0. And finally, this term here, the negative 1 comes out the front, giving us a positive value of theta. So it becomes theta and then 1 off the power, negative 2, sum I equals 1 to n of xi gamma ln xi. And of course, we can rewrite this as 1 on theta squared, I equals 1 to n of xi to the gamma ln xi. And we found our expression for the second derivative. So, now I've found the first and second derivatives, we now need to actually solve for our maximum likelihood estimate. So, our maximum likelihood estimate, again, we're going to assume that that gamma is known for this particular problem. So we need to solve for the derivative of the likelihood function evaluated at, gamma theta given x bar, close the brackets, d theta evaluated at theta equals theta hat is equal to 0. And in this particular instance, this gives us the value. So let's take our first derivative that we had before. Here it is here. We came up with it before. Copy that across. Paste that in. So this evaluated, of course, not at theta, but at theta hat, has to be equal to 0. We can do some simplification here. The first bit of simplification is to move the negative n on theta hat to the other side. And I'm going to rewrite, so 1 on theta hat squared, sum I equals 1 to n xi to the gamma equals n on theta hat. And then if we multiply both sides by theta hat squared on n as a side, then what we end up with is, if and only if, 1 on n sum of I equals 1 to n of xi to the gamma is equal to theta hat. And we've come up with our maximum likelihood estimate for theta hat. Or, alternatively, we can write theta hat is equal to log xn bar, where xn bar is by definition, or shouldn't say log xn bar, apologies, should say xn to the gamma. So where xn to the gamma bar is by definition the average value of xi to the gamma. And it's a bit of a shorthand definition, but so be it. So, now that we've come up with this particular expression, we need to prove that this is in fact a maximum. To prove that, we need to use the second derivative test. So let's evaluate the second derivative, the second derivative of the log likelihood function, gamma x at d theta squared. Again, evaluate at theta equals theta hat is equal to, what is our expression that we came up with for the second derivative? I believe we had it here. Yes, it is here, in this part here. Copy that across, and I forgot to put the second derivative terms. Apologies for that in the earlier part of the video. So we're going to take those terms, paste them in here. Hat, and don't forget that this is evaluated at, in particular, 2 on theta hat cubed. Now, one thing to note is this is a bit of a challenging problem to prove that this is less than or equal to 0. That proves that it is in fact a maximum or a local maximum. But notice that this xi to the gamma is up here in this expression. And in fact, this sum of I equals 1 to n of xi to the gamma, if we brought the n to the opposite side, we'd actually come up with a version of that sum which can be expressed in theta hat. In other words, this is n on theta hat squared minus 2 on theta hat cubed times n theta hat by definition, or by definition of what our theta hat has to be evaluated at. After a little bit more simplification, this becomes n on theta hat squared minus 2n on theta, 2n also over theta hat squared, after there's a cancellation with this theta hat and the 2 there. And then finally, this gives us is equal to negative n on theta hat squared, which is less than or equal to 0. And so we have proved that it is in fact a maximum, this maximum likelihood estimate. And so that is in fact the maximum likelihood estimate for theta if we had a known value of gamma. Now, I did promise you that we'd use some of the other partial derivatives that I derived. In particular, suppose that gamma is also unknown. So, if gamma is also unknown, and I've clearly forgotten a partial derivative there as well, if gamma is also unknown, then we need to solve for when the partial derivative with respect to gamma copy is equal to 0. So let's do that now. So I'm just going to paste that in. So we're interested in the partial derivative of gamma theta given our data x bar on delta gamma is equal to, evaluated at theta or gamma hat theta hat is equal to 0 if and only if, now is our expression here, put on the hats for everything. So this becomes theta hat. And now that has to be equal to 0. And what I'm going to try to do is come up with an expression here. So we know what our theta hat was before. So let me first put that to the other side. In fact, I'm going to do a little bit of rearranging. Sorry, I forgot the hat here for gamma. What I'm going to do is I'm going to get all the terms that have parameters and all the terms that are independent of parameters. So in this case, this is the only term that are independent of parameters. So I'm going to move all the other terms to this side of the equation. So this becomes 1 on theta hat, sum of I equals 1 to n of xi to the gamma ln of xi minus n on gamma hat is equal to the sum of I equals 1 to n of log xi. And for your information or for your benefit, I'm going to define this particular term, log xn bar, as defined by the average value of the log xi's. Or alternatively, I could rewrite this as n times the average value of the log values is also equivalent to the sum of the log values. And that I'll use that to replace that final term there, FYI. Now, our theta hat we evaluated before. We said that our theta hat, apologies, perhaps it was on one of the other pages, or maybe it was down below. Here it was. Our 1 on theta, or our theta hat, was by definition the average value of the xi's. So I'm going to copy that and I'm going to paste it here, and then we're going to take 1, put it in white, it'll be 1 over this entire value, if and only if, and then we've still got I equals 1 to n, xi to the gamma, ln xi minus n on gamma hat. Gamma hat is again, in this particular instance, is going to be equal to n times log xn bar. If and only if, in this particular case, this 1 on n can be taken, because that's 1 over 1 on n, the n can become part of the numerator, so it becomes n on the sum of I equals 1 to n of xi to the gamma, and of course we have I equals 1 to n of xi to the gamma ln xi minus n on gamma hat. Don't forget all the hats everywhere. I keep forgetting to put my hats. ln log xn bar. Don't forget the hats everywhere. Poor habit of mine. Now, one final step here is we're going to divide each side by n, which will leave us with the following expression. The sum of I equals 1 to n of xi to the gamma hat ln of xi all over the sum of I equals 1 on n to xi lambda hat minus 1 on lambda hat is equal to log xn bar. Now, of course, this isn't a closed form expression for gamma. However, this is an expression for gamma which, using numerical techniques, we can actually solve for the maximum likelihood estimate. So there you have it. We've been able to derive an equation that we can solve numerically for lambda hat, also for gamma hat, and for theta hat, we were able to solve for at a closed form expression. It was up here, and this is the case here. Now, of course, if you remember the beginning, the parameterization was we had theta is equal to lambda to the gamma. So alternatively, just at the very end here, if we go to our expression for theta hat, copy that for your own benefit, I suppose. Again, paste. We had 1 on that is equal to theta hat. Remember, this by definition was 1 on n, I equals 1 to the n, xi to the gamma is equal to, in this case, we can write theta or lambda hat to the gamma, which leaves us with our lambda hat, if we were to use the alternative expression, would be 1 on n sum I equals 1 to n of xi to the gamma, all to the power of 1 on gamma.